Okay, let's kick it off. Thanks everybody for joining. This is community meeting number 10. So let's start with a quick agenda. We have an awesome talk from Evan on linear slash non-destructible types in Mojo. And then we have a couple of Q&A questions that we're going to go through. So I'm going to hand it over to Evan. Oh, I think you're muted.
How about now? There we
Yep.
go.
You know.
Cool. Yeah, give me just a second. I'm trying to figure out how to open speaker mode on this thing again. There we go. Okay, y'all see my screen?
Yep, we can see it.
Cool. Okay, so yeah, I'm about to talk to you all about linear types. And oh yeah, this is my first time here in this community meeting, so super happy to be here, and I'm super glad to hear all your thoughts on what I'm about to talk about. So yeah, we're going to talk about linear types. I also kind of call them explicitly destroyed types or explicitly destroyable types, kind of depending on what mood I'm in. Um,
Sorry to
and
interrupt, but Evan, do you want to introduce yourself a bit for folks who don't know you? Um,
yeah, sure. So I'm Evan. I'm a Mojo compiler engineer on the Mojo team. So I've been working a lot on the compiler internals and also a little bit on figuring out what features go into Mojo. So yeah, I'm pretty excited about that. Yeah, that's pretty much me. Um, so I'll explain what linear types are, but before I go too deep into it, I want to kind of show you all a riddle. So can you spot the problem with these comments? The first one is saying you have to remember to call join or detach on a thread before it goes out of scope. Sorry, let me mess with the screen size there. Okay. Yeah. The first one is saying you have to remember to call join or detach on the thread before it goes out of scope. The second one is saying, hey, caller, I am returning to you a promise. Please remember to call set value on it. The third one is saying remember to decelerate the car before you stop driving. And the fourth one is saying remember to destroy, or sorry, before you destroy an entity, remember to remove its ID from a location map. So without knowing any of the context of any of these, you can kind of tell that the common problem is that they all rely on the programmer to remember to do something. And we humans are like not great at remembering to do something, especially this human. And modern compilers don't really help us that much. They're great at telling us what we can't ever do, like with static typing, but they don't really remind us to ever do something. And we can kind of get halfway there with our AII, but that really doesn't help with any of these examples. So we're going to talk about what's a linear type, how it prevents bugs like these, and then the third thing, I'm going to show you all the linear type's hidden superpower. That kind of blows my mind, and I can't wait to get to that slide. And if you have any questions, just remember the number in the low right there, and I'll answer them at the end. Okay, so what's linear? A linear object must eventually be consumed exactly once. That's the normal definition I usually see on the internet, but it's kind of a terrible definition. And so if you ever see a definition like this, I recommend ignoring it because it really doesn't capture the potential of linear types. So I recommend ignoring it. And we're going to use my definition instead for now. My definition is a linear object can't just go out of scope. You must eventually explicitly destroy it in a specific way. And I'll show you what I mean with this basic example that I think really shows how they shine. If any of you have used C++ STE thread before, you've run into this and you you probably have battle scars from the encounter. Um, if you accidentally let this thread go out of scope, like this code on the right, without calling join or detach on it first, its destructor doesn't know what to do. Does it wait for the thread to join? Does it detach and let it run in the background? The poor destructor doesn't know, so it, it does the reasonable thing, which is panic and crash your entire program by calling std terminate. So there is, for those of you who know C++ really well, there is a half solution called std jthread. But that's kind of a half solution, and I'll show you more about that after we show how linear types solves it in a way that, in my opinion, is a little bit better. Okay, so it would be nice if we had something like this Mojo code on the right. We have a thread in a local variable named t, and when we let it go out of scope, the compiler tells us can't delete t, call, join, or detach instead. And it would be pretty nice to catch that at compile time like that. Okay, so how do we make that happen? Well, let's look at the definition of struct thread right here. And first, notice this explicit destroy annotation. This means that there's no destructor. An object of this type can't just go out of scope. And right after that, we specify a hint to show the user in the error message when they accidentally do let it go out of scope. But the user has to get rid of it somehow, so let's have some methods that take ownership of the object using this owned keyword. And this isn't new. Like for those of you who know Mojo really well already, it's just a keyword that means it's a pointer to data that you now own. And this method does some things, and then it uses this new proposed destroy keyword to finally destroy it. Now, join and detach, I want to emphasize here, join and detach are just regular methods. It's the destroy keyword that would be special. And a type's user, like that function foo, they wouldn't use destroy directly. It's really one of the type's own methods that uses destroy when it's finally ready to finally explicitly end the object. And you can kind of see how like, okay, if the user doesn't call destroy, if they can't call destroy, and only a method can call destroy, then that means that the user is forced to eventually call one of these methods. Okay, so yeah, some details on the destroy keyword. It'll eventually, well, it'll end the object. It'll call any destructors on any normal members inside it. And if there's a linear type inside this linear type, then it will show any error if you haven't handled that member linear type. And that's kind of weird, and feel free to ask questions about that afterwards. So yeah, we now have a linear type, or in other words, an explicitly destroyed type. Okay, so how does the user fix their function now? Well, they have some options. They can either call a method that takes it as an owned argument and destroys it, like, you know, a call to detach. And more on this. See how it says, yeah, sorry. I'm getting confused by my notes here. Another option is to postpone destroying this thread and instead maybe add it to some longer lived data structure like this threads list. And whoever owns this list of thread, the compiler helps them remember to not let that go out of scope, to instead do something like drain the list and do something with all those threads before that list goes out of scope. A takeaway from this slide is that thread is linear, so a list of thread is linear too, and the compiler will make sure that someone will handle those threads in that list. And I'll talk a little bit about how it is that a list is linear if the member thread is linear in a bit. Okay, so the last option is to return t caret, which means, of course, move t into a return value for our caller. And now the caller is responsible for figuring out what to do with this thread. Now they have to call either join or detach or move it to somewhere else. So that's the first example of a linear type. The compiler ensures that you eventually actually decide when and how this object should go away. You could say that it ensures you eventually make a decision, and that's a clue to the linear type hidden superpower that I'm going to get to in a bit. It ensures you eventually make a decision. Okay, so there are a lot of types like this where the compiler shouldn't assume when and shouldn't assume how you want to destroy your object. And I mentioned JThread earlier. JThread tries to solve this problem by just assuming that you want to join. But this can be harmful, like in this code here, where we have a loop and we accidentally let the threads go out of scope too early. And you can see by using JThread, we've opened ourselves up to a bit of a risk where we accidentally forget to do something with it, and we accidentally serialize this loop that we were hoping would be parallel. So as you can see, even though RAII was, you know, a huge step forward and it can solve some things, it doesn't really help here. Linear types help in much more situations. They take it a little, I like to say that it takes it a step further than RAII. You specify exactly when and exactly how your object goes away. And also, if some of you are wondering why C++ doesn't do linear types, it's because of exceptions and stack unwinding and stuff like that. And I'll talk about that in a bit too. Yeah, okay. So that was one example, but there are a ton of ways that linear types help us. And let's talk about that second one. Don't worry, we won't go through all of these. We don't have enough time, but I'll just talk about my favorite ones. Yeah, let's talk about this second one. So this is another example, which also coincidentally has something to do with threads. If you want to give a value to another thread, you often use a promise. And when you call set value on it, the other thread can use the value and, sorry, can see the value and use it. But if you forget, like in this code, then the other thread never gets the value. So if only something could help us remember to call set value. So here's the Mojo equivalent. You can see how it shows an error if we don't call set value. And let's see the promise struct now. Here's the promise struct with the explicit destroy annotation to opt in to it being a linear type, so it can't just go out of scope. And there's us specifying that error message. And of course, we got to give the user some way to get rid of these things. So we give them this set value method, which takes an owned self and also requires the value argument, right? And does some ... things, and then destroys the promise. So how do we fix that error message? Well, once again, we can move it into a method, or we can postpone it by moving it somewhere else. But let's say that we do call set value. And oh wait, we realize now, we never actually calculated the result. So let's do that now. There we go. Okay, so it's kind of like RAII, but the destructor has a name and can require arguments. So, and here's the second clue to the linear type hidden superpowers. The compiler ensured that we eventually called set value, and it kind of also ensured that we eventually calculated that result right there. So that's the clue. Okay, last example. So continuing the theme of threading, here's an example with a future that will contain an important linear thing. Perhaps it represents a pending request whose response they need to act on, or perhaps it represents the airplane's current flight that they need to correctly land. A user shouldn't just let this thing go out of scope. Fortunately, they get an error about it. And if you're curious, this is how the future struct would be defined. So how does the user fix this error? Well, like the hint says, they can call f_get, and hey, they get the result out of that, which is nice. Like you see the thing equals f_get. It's almost like linear types ensured that we got that result and took ownership of it. It's kind of like RAII, where the destructor returns a value too, you could say. Oh yeah, this is the third clue. This is the third clue to the hidden superpower. It also ensured that we eventually took ownership of that result thing, like I said, but that's the clue. Okay, so from these, you can kind of see a pattern emerging. And no, it's not that they all have to do with threading. That's just a coincidence in the examples I chose. So these are the three things that linear types did for us. They ensured we eventually made a decision, like about those threads. They ensured we eventually calculated and gave a value, like to that promise. And they ensured that we eventually took ownership of a value, like from that future. So these hint at something. And if there's one thing I want everyone to take away from all this, it's the linear type hidden superpower at long last, which is that with linear types, you literally control the future. You can craft your linear types and their methods to ensure that specific things eventually happen in some order at some point in the future. This is amazing if you're making an API for other people to use, by the way. Yeah, and so like you don't know when these things will happen. You don't know when they're going to call these methods that are blessed to destroy this object. But as soon as you create that linear object, you know that those decisions will be made, that data will be calculated, given, or taken, and destroyed in the correct way. And you can combine these in interesting ways to help your user correctly use your types. And I'll show you in a few slides just how powerful this is when a simple linear type single-handedly solved 3 cache inconsistency bugs for me. Yeah, so, but before I talk about that, I want to nerd snipe everyone. And I'm going to talk about all of these ways that I think linear types can help us, all of these situations. And for most of these, I'll just quickly lay out the scenarios and I'll leave their solutions as an exercise to the reader. But ask me in the Q&A after if you want to know specifics. Okay, so we saw already how they help with threads, futures, and promises. They can also ensure that you correctly decelerate before ending your current driving session for a car, for example. They can also ensure that you stop a rocket booster correctly, depending on the situation, not too early, not too late. They can ensure that you handle a failed request rather than dropping it on the ground. They can make sure that you actually update your database row to reflect the outcome of the calculation. They can prevent node leaks. And this one's a little arcane, and I wish I could, go into this a little more deeply, but I'll leave it vague for now. They can prevent node leaks when you accidentally drop your owning handle, so to speak, and cause orphan nodes in a vector-backed collection. They can ensure that a message is correctly handled and not forgotten in an orphaned channel, so to speak. This is a common problem in Golang, for example. So I'm pretty excited that we can actually solve this with linear types. And this one blew my mind so spectacularly that it gets its own slide. So this is something from Vale. If for those of you that don't know me, I also work on my own personal project called Vale, and it's where I implemented linear types in the first place about 3-4 years ago, and that's where I actually saw this happen, and so that's why I'm excited to bring it to Mojo potentially. So yeah, here's an example from Vale, and I'll show it in Mojo syntax just to be merciful to you all. So here's a couple structs that I was using for a game, and I'll explain what they do. This is the central list of entities in the level, and we wrap it in this live entity list struct right here. And we have an add method and a remove method. Nothing surprising so far. But this is interesting. The add method returns two live entity handles that refer to the entity we just added. Now, both of these are instances of this live entity handle struct that has its index in the list and explicit destroy on it, so they can't just let it go out of scope. It looks like the only way to get rid of them is to eventually give them back to this remove method. Yeah, so these handles only exist while the entity is still in the list. So where did they go in the meantime? Well, in that case, they were in some maps. They were in a location to entity handle map to tell who's at what location, and also a map of team to what entities are in that team. And here's some comments just to emphasize that. So what were the implications? Well, the first one is that if you know, like if you have a live entity handle, or if you have a borrow reference to it, you know that it is still in the live entity list. It's kind of like weak pointer, but it's more general. Like weak pointer, you can know whether something still exists somewhere. But with this shows that if we have a handle, we can assume an arbitrary property of a distant object, such as its membership in our source of truth list over here. It's kind of like spooky knowledge at a distance or linear entanglement, but we still have to come up with a cool name for that if this happens. Also, thank goodness, dangling live entity handles are impossible, and that's because you must take the handles out of the maps before you can use them to remove the entity from the list. So the maps can never get out of sync with the list because of this. In other words, we just solved inconsistency bugs for these collections by crafting our linear types in a certain way and making use of these linear type superpowers. And like maybe I'm just a language nerd. I mean, we know I'm a language nerd, but that's ridiculously cool to me. Someone said that the hardest two problems in computer science were naming and cache invalidation, and I like to think that now there's only one problem now, naming. So this blew my mind when I discovered this. I thought I was just making a struct linear on a whim to see what happened, but I followed the ripple effect, seeing what Vale was trying to show me, and suddenly 3 places in the code kind of lit up, and it showed exactly where I'd accidentally removed from only some of the collections and not all of them. And I sat back and I was like, holy crap, like a compiler just did that. That's crazy. And I should say, like, this doesn't solve every bug, and this isn't a panacea. Like, for example, you can still hand into mismatched handles, for example. But in my opinion, that's a much better problem to have. Like, that's a much easier problem to see, and it's a much easier problem to solve, rather than, state inconsistency problems, which are the bane of my existence. Okay, so one last thing to freak people out, and I don't expect anyone to understand this. Like, this is like deep, dark, arcane magic, and I'm not explaining it very well. But if you think of these two handles as references, then this is kind of like some sort of non-scoped borrowing or compile time reference counting or something, because like these are references that just escape into the wild, right? But then you kind of put a constraint on the universe that like people have to do things, like other functions have to orchestrate it somehow so that these two handles make it back to me so that I can be sure to destroy them at the same time I'm removing it from the list. And that kind of rhymes, that kind of echoes with like reference counting in a way. But this has no runtime overheads. This is like compile time reference counting. I know I'm not making any sense about that. So like feel free to ping me on Discord if you want more insights into that one. Okay, so back down to earth. Yeah, so fitting this better into the context of Mojo. We already know that Mojo kind of has, like, I don't want to say Mojo has RAII, right? Because a lot of people think that you have to, like, it's like C++ or Rust style RAII, where an object is destroyed at the end of the scope, but it kind of has our AII in a way, but in the form of ASAP destruction. Um, and for those of you who don't know what ASAP destruction is, um, yeah, it means that Mojo inserts destructors not at the end of the scope, it inserts them as soon as it can. In this case, it sees that the last use of ship is right here, so it inserts the del destructor call right here. Um, and this is awesome, uh, but uh, it fits in with linear types in a certain way. And so in this slide, I want to talk about how linear types fit in with that aspect of Mojo and also with statements and async await. So ASAP destruction is, in my opinion, really good for freeing things, right? Or like releasing some buffers on a GPU or doing things that don't have any non-local effects. That have any like complex side effects in the system. I think ASAP destruction is good for that. And with statements are really good for when you want to make something explicit. We know that. With statements, we'll delay something's destruction until the end of the scope. That's great. But it only works in the current scope. And it's kind of the same thing with async await, but in a concurrent way. There's no way to ensure that something happens past the end of your current scope. And that's where linear types fit in. And I also kind of think that linear types would be good for when we want to ensure destruction happens uh, in a way that has complex side effects because it's explicit, right? So if something's destruction has side effects in the rest of the system, I think it should be explicit. But that's my own personal opinion. And I kind of want to hear what you all think about that. Also, I don't think I have enough time to talk about the container problem because I think I'm running long.
No, you have plenty of time. You can talk
Oh,
about it
okay. Cool. How long do I have?
however long you want.
Okay, awesome. Yeah, okay. I'm going to keep geeking out about the container problem then. Um, so some of you are probably wondering, how do we make this work for like list, right? Or I guess, okay, I'll stick to the slide. Okay, box for now. I'll talk about list in a bit. Okay, so how do we make it work with generic containers like list, optional, dictionary, box, and so on? They have their destructors, but their elements might not. So what happens? In other words, just to clarify the problem, we have a box of T, which has a del destructor method, which usually calls T's del destructor method. But if T doesn't have one, like if it's a linear type, what happens? We get that error, right? So the answer is to use conditional conformance, where our box only has a del method if T has a del method that we can call. Something like this. And this I implemented in this Vale, but I don't have it implemented in Vojo, and I don't Vojo. I don't have it implemented in Mojo yet. But this is how it worked in Vale, and I'll keep showing it in Mojo syntax. So our delete only exists when T has a delete. Sorry, destructor. I shouldn't say delete. And this approach works for linear types. Like we apply it here to the del method, and that makes it work for containers like this. So I want to restate something to make it super clear what's going on here. There's two ways to make a linear type in this kind of proposal here. There's using the explicit destroy annotation, and there's using a conditional destructor like this. If we have a conditional destructor, that means that when the destructor doesn't exist, the type is a linear type. And that's what we see going on here. The other way to make a linear type is to use the explicit destroy annotation. So yeah, Mojo will likely be a bit different in the syntax than this, because, that's something we'll have to discuss. And it'll be using a trait instead of asking directly for whether this function exists. But it's close enough to how I did it in Vale a long time ago that I'm pretty confident it will work. Yeah, so that's pretty much the end of the content I had. I've got a few notes here. Yeah, one of the big open questions is whether the linear types, whether the benefits of linear types are worth this extra thing we have to keep in mind for our destructors, for our containers like this. And it's something I want to get all of your thoughts on, because like it's really hard to see what kind of an effect this feature could have on a language like Mojo. without actually trying it. And like, since I'm on the compiler team, I managed to like, hack up a little prototype of it on a weekend, but I haven't yet figured out how it could affect the architectures of our program. So I'm also going to be relying on the crystal balling skills of all of you out here to kind of think about like how could this affect Mojo programs? Yeah, okay, so the other note I have here is that there is something there's something I didn't get to talk about in this talk, which is super interesting to me because I'm a language nerd. Um, but some of you might know what I'm talking about here, and that's that linear types have an interesting interaction with borrowing, like Mojo's going for. And oh man, can I? Yeah, I'm gonna go back to that slide. Uh, oh yeah, it's this slide. Yeah, okay. So here on this slide, I showed an add and remove method for the live entity list struct. If you think about implementing a get method, now normally the get would take an integer index, right? And it might return an optional reference to an entity. And it's optional because if the user hands in an index, like what if they handed in something out of bounds, right? So that's why it would normally have to return an optional of a reference to that entity. But hold my beer. Here's what I'm thinking. If we also make a get method that takes in not an index, but a reference to one of these live entity handles, it's kind of like we can use that as proof that that entity is still in the list. So we no longer have to return an optional reference to the entity. We can just return the reference to the entity. So it's like we've kind of solved the lookup after remove problem, right? The user can't accidentally hand in an index to an entity that no longer exists, which means that our get method can return not an optional, but an actual reference to the entity. So it's something that I think could like have a few like runtime, speed implications, a lot of reliability implications. We've narrowed out an entire class of bugs there. But yeah, if anyone wants any more details on where I think I'm going with that, just ask me in the Q&A. Okay, I'm losing myself in the slides here. Yeah, so I think I'll stop here for now. But yeah, if anyone has any questions, feel free to ask them. Here's some good unanswered ones that I didn't answer in the talk. Uh, if you want to talk about these. So yeah, that's all I got for now.
Awesome. Thank you so much. Any questions for Evan?
Yeah, awesome talk, Evan. Thanks so much, man. That's really cool. I was just wondering about, like, say, for unsafe pointer, are you able to use a linear type on that to make sure that it gets freed at some point?
Yes, yes, and I really like that because like when you're dealing with unsafe pointers, you're often dealing with things that don't fit well into the, safe type system in general. And often those things have, explicit effects on the system. So yeah, like in principle, you can make unsafe pointer into a linear type. Like you could change the language to do that, make all unsafe pointers into linear types. I don't know if I would make all unsafe pointers into linear types though. I think the right approach in that case might be to make a linear struct that's a wrapper around that particular unsafe pointer. That's like crafted to your specific use case. Like so, for example, if you have a unsafe pointer to, oh, I don't know, I'll fall back on my normal example, a spaceship, right? If you have an unsafe pointer to a spaceship, right, you might want to make a linear struct wrapper around that unsafe pointer called unsafe spaceship pointer, and that will enforce that you correctly destroy that spaceship in the particular way that makes sense for that situation in that particular unsafe pointer. Does that make sense?
Yeah, sweet. Like for circumstances where you might not want to free something, like just let the program free it at the end of, like, once it finishes executing.
Yes, yes, exactly. And that's one of the strengths of linear types is that like they make it so you don't have to just free something in a destructor. Like because destructors and like the del method are mainly for cleaning up. And I think they should stay that way because of ASAP destruction. The language moves the destructor as soon as it can, and sometimes that's surprising. Like I think destructors in Mojo should only be for cleanup. Anything more advanced than that, I really think should be in a either with statement or a linear type. But that's my own personal preference. I'd love to hear what the rest of you think.
That's really cool. It'd just be interesting to put it like on unsafe pointer and see all the places in the code base where we're not freeing properly.
Yeah,
I
yeah,
think we'll
I
find a few.
agree.
I have a question.
Mhm.
How should we think about like the main downsides of linear types? Obviously, you made a lot of, points about why they're awesome and the hidden superpowers, but what would you say is like the main reason that more languages don't have them?
Yes, I'm so glad you asked that because I totally forgot about that. I was going to talk about that and I didn't. Um, so the main reason that, for example, C++ and Rust don't do this is because they made, in my opinion, well, I can't really call it a mistake because they had really good reasons and it does give them benefits. But I think they made a decision that Mojo could improve on. Um, their decision was to conflate exception handling with normal control flow. So in C++ and Rust, right, if function A calls B calls C calls D calls E, and E, like at the very leaf function, E throws an exception. That exception is going to like bust its way through all the stack frames until it gets back up to main, or a try catch block or a catch unwind or whatever it is. And because of that, because this stack unwinding needs to clean up any objects in its path, it needs to clean up any locals that exist. Um, it's going to need a way to clean them up. It's going to need a function to call to free all these buffers that are in local variables that are pointing to the heap and so on. And so it needs a zero argument destructor to call. And that's why C++ and Rust, they saw that situation and so they decided to use the destructor, which they were also already using as a way to just clean up things when they go out of scope normally. I think that they should, I think what we can do differently, it's complicated because like Mojo, as far as I know, Mojo doesn't have panics. Someone can correct me if I'm wrong because I'm new here, right? Um, but since Mojo doesn't have panics, it doesn't really have that problem. It doesn't have exceptions. It has errors, which are much more explicit. Uh, we don't have to have a zero argument destructor, so we don't have that problem. But in going back to the case of C++, if they, for example, deconflated, if they decoupled exception handling from normal going out of scope, they could have had a separate on panic handler, or I guess for C++, it'd be called on exception handler. And that would be called when an exception is blasting its way through the stack frames. Same with Rust. It could be called on panic there. In Vale, this was what I was planning to do with Vale, is have an on panic handler called specifically for stack unwinding. And then the object is free to choose for normal control flow whether it wants to do something like ASAP destruction or linear types. So in a way, we decouple exception handling and panic handling and stack unwinding from normal control flow handling, which can be accomplished really nicely with ASAP destruction or linear types. Yeah, I hope that makes sense.
Yeah, that does. Thank you. A couple questions in the chat. Linear types have been around in the programming language world for over 30 years. Is there any example of a non-toy linear language that would be a helpful case study?
Yeah, yeah. Thanks to whoever answered Vale to that. I appreciate that. Um, Vale is depending on how you define it, Vale could be called a toy language. Like I don't call it a toy language. You know, it's working on it for a decade and it's 140,000 lines, but it doesn't have that like widespread adoption, and that's important here because uh, that means that we don't know how linear types will do at scale, right? Like for example, there's something I noticed architectural benefits and costs to using them in Vale. One of the costs was that it made our generic functions a little bit trickier for these generic containers like box, list, dictionary, and so on. Another potential drawback that I don't know how it's going to do at scale is a type being linear seems partially viral. Like you saw how if a thread is linear, then a list of thread becomes linear. Well, sometimes whoever it is that owns the list of thread, they're just like a class or a struct somewhere, and they don't know what to do with this list of linear with this list of threads. And so they make themselves linear. So they leave it to their owner to figure it out. In other words, what I sometimes saw in the little prototypes I did in Vale is that this linearity would kind of virally trickle up to the root container of the entire program. This didn't always happen, but this sometimes happened. And in all the cases that I saw, this was actually a benefit, but this can have downsides. Every viral constraint has downsides. Async await, linear types, sync and send in Rust is an example of this. So I really like your example of like, have there ever been any non-toy linear languages? No, I think for us the answer is no, and so we don't know how this would turn out. And so that's why I really want us to like consider carefully what this feature could be like, what it could be like specifically in Mojo, and what it could be like in the real world in Mojo programs, and for various different architectures that might be in the wild. Yeah, I hope that answers the question.
One other question in the chat. Is there a point at which the type system gives up, and will there be an escape hatch? For instance, if I have a bunch of very messy rules around when objects are removed from a collection and freed, such as when I get a message from another server that says to free UUID X, do you attempt to prove that the list is empty before I free the list?
Oh, that's a super good question. I love that one. Yes, this is a case I ran into in Vale, and it took me like, I swear, a week of bashing my head against the wall before I figured this one out. Um, yes, the answer is yes. The list, we do have to prove that the list is empty before we free the list, and most of the time it is, the user would call a function called drain. I think I called it drain or drain all. Um, And that is a method that consumes the list and also calls a user-specified function for every element in the list. And that wasn't the only option. The other option was a function called like assert empty, it was called assume empty, and that consumed the list and also did an assert to make sure that the list was indeed empty. So I expect that these kind of like escape hatches, like assume empty, will kind of naturally pop up in the APIs for these linear types, like they did for list in Vale's case. But I think even past that, like that's an escape hatch that the definer of list can define if they are looking forward enough to see that the user will need this escape hatch. I see some merit in the argument of maybe we should go a little bit further than that. Like maybe we should just allow users to call the destroy keyword on any type. I and it sucks because like saying that means that I'm suggesting we offer a feature which undermines the guarantees that linear types give us. But I think in real world code bases, situations often arise where like it's extremely difficult to work within a very strict system. In fact, we saw this in Rust all the time. This is why Rust has refcell and RC and arc and mutex and RW lock. These kinds of like constraints are very helpful until the last 5% of use cases where it's like, oh, but the real world doesn't work as well as, math and linear types do. So I personally am leaning towards recommending we have the user be able to call destroy from anywhere. Maybe we could have some like extra rules of thumb, like, hey, if you're using destroy keyword outside of the class that defined it, like please put a comment explaining why. And like we've seen a similar recommendation, for example, in Rust with the unsafe blocks. Like if you use an unsafe block and you want to break out of the strong type system guarantees of borrow checking, put a comment over it. And that's like, I think there's linters that enforce that in Rust too. So yeah, that would be the escape hatch I recommend. I'm just going to reread the question real quick. Yeah, I think that answers it, but let me know if that didn't answer it.
There's actually one other question that was submitted ahead of time, and I was gonna share it in the Q&A section, but we can just do it now. So I read your blog post about the 7 arcane uses of linear types. I'm just wondering what the differences are between the approach to linear types in Vale compared to linear types in Mojo. Would we be able to use linear types to prevent leaks, for example? By the way, I love your blog. And that's from Richard. I know you covered some of it, but
Yeah. Oh my God, I love that. Yeah, so the differences between Vale and Mojo. I think at a basic level, the approaches would be the same. Um, there's there's one big difference that I found so far. Um, yeah, there it is. So right here, this is veil thinking right here. This is not how I think we would do it in Mojo. And the veil thinking here is that it says where exists t colon colon del. Now, veil can do this thing called concept functions, um, where you can enable a function if a specific you can enable a function like this destructor del if another function exists for a given type. And that's because in Veil, like there's no difference between methods and functions. They're all just functions, right? So instead of a Mojo style thinking of asking if a type has a method, Veil asks if a function exists anywhere in the visible scope. Um, and on top of that, Mojo doesn't even think in terms of functions like this. It thinks in terms of traits. This line in Mojo would probably look something like where T implements trait implicitly destructible, for example. And implicitly destructible might be a trait that just defines the del function. That's how Mojo works right now, and I don't think we should change that. I don't. That was a bit of an adventure in Veil. That was an experiment doing this concept functions thing. I think in this case, Mojo will want to put a constraint on this to say where T implements some sort of trait that defines, a delete method. So that's the only big difference that pops out between Veil and what I think we could do in Mojo. Um, right, Mojo, as far as I know, doesn't have stack unwinding, so it doesn't face the whole, do we need a zero argument destructor problem? Veil would have a difference here. In my mind, Vale was going to do some crazy things with like software transactional memory, and I had all these like crazy plans on the wall, uh, and so Vale would have an on-panic handler for that case. But luckily, Mojo doesn't have that problem, so I guess that would be another difference between Mojo and Vale. Someone in the chat says Mojo has conditional methods. Yes, yes, it does. It doesn't have them for destructors yet, uh, and does think. Uh, it does think in terms of implementing traits for these other methods already, which is really nice. So yeah, that'll fit in really well with Mojo's existing conditional methods. Yeah. Okay, so there was another question. How do you handle something? No, sorry. There was a second half to that question you said, Caroline. Can you remind me what that second half was?
And I think you did kind of touch on this before, but would we be able to use linear types to prevent leaks, for example?
Yes. Yes. And it gets even better actually. So like regular ASAP destruction and regular RAI, they kind of solve leaks, right? But I'm going to blow people's minds here. They actually, how do I say this? There's actually a class of hidden leaks that RAII has not yet solved, and ASAP destruction doesn't yet solve. And I'm going to try and TLDR this as best I can. If you imagine a doubly linked list implemented in something like C++, you would have a unique pointer, an owning pointer, from each node to the next one. And all of the back pointers would be regular non-owning, just raw pointers. But we see a certain phenomenon when we try and translate that C++ doubly linked list into something that uses a borrowing system, like Rust or Mojo. And what we see is we end up putting all these nodes in a vector, an array list, and then and then a node will refer to other nodes via indices, indexes, integers. And there's a risk in there in that we lost our AII's power of ensuring that every node is eventually deleted, right? There's certain ways you can mess up a vector-backed doubly linked list that you can't mess up in C++. And that's that we can accidentally mishandle the owning index, so to speak, of a given node. Linear types actually help that. With linear types, you can have all of your doubly linked list nodes in a vector, and what you would do is you would have every node would have um, an optional linear wrapper around an index that refers to the next node if it has one. And because that linear wrapper around the index is linear, the optional uh, becomes linear. And so you're forced to handle it in various places in the code, which eventually means that you can't actually accidentally orphan a node in this vector-backed doubly linked list. If you've ever heard someone claim that Java can have memory leaks, this is also what they're referring to because this can happen in Java too. You will often have a central canonical source of truth list for all of your Java objects, right? And someone else is responsible for removing things from this list, but they forget, right? Because they forget to call dispose or they forget to do something. And that's a case where even Java can have something like a memory leak because someone didn't correctly handle their responsibility for removing something from a list. And linear types are great at tracking responsibility. Heck, they enforce that you eventually call methods. That's exactly tracking responsibility. So yes, linear types handles memory leaks and other kinds of leaks in a way that goes even past RAII and ASEP destruction, which is pretty cool. Yeah, I'm so glad I got to ramble about that because that's one of my favorite things about linear types. Okay, so there was a question in the chat.
Here's one from Gabriel. Can the readiness of being destroyed be encoded in the type of object as a parameter?
Oh man, you're going into some deep dark arts here. Yes, yes, it can. So uh, if so, yes, and the way this can happen is if we have conditional conformance where a struct can conditionally implement a certain trait. Okay, actually, my brain's kind of falling apart on this one. But I think what you're kind of getting at is some sort of type state programming. I just want to say that at least. Type state programming is where you get closer and closer and closer to making your type system really represent all the possible types, sorry, all the possible states of a certain state machine. And one thing that I think is going to happen if we introduce linear types is that people will have for example, they will have a struct representing a rocket that is currently in flight, right? And like maybe this rocket is delivering, snacks up to the International Space Station for these astronauts, right? And so you'll have a struct that represents this rocket that is currently in flight, right? And then at some point, oh, and you'd want to make that linear, right? Because you don't want to just drop this rocket on the floor, right? And you don't want to accidentally forget to go through its whole shutdown sequence. So that would be linear, and the only way to get rid of that linear type will be to initiate its booster shutdown sequence. And once you initiate that booster shutdown sequence, it'll consume that in-flight rocket and produce a currently shutting down rocket. And that's literally what the struct would be called, currently shutting down rocket. And then eventually you could only destroy that by calling land, right? Once it actually gets to the surface of the moon or the ISS or whatever. Now, these are differences. I just described different entire structs, but there are ways that you can represent these differences not as entirely different structs, but instead as a input generic parameter. And I think that's kind of what you're getting at, Gabriel, is encoding things in the type of the object that could influence whether or not we can destroy things. And I think we can do that. I don't know if Mojo has the machinery for this yet. Gabriel, you know better than I do. But I think if we can make it, if we can take in an input generic parameter of a type and then make our spaceship struct implicitly or explicitly extend that type that we're given in, I think we could do something like that. I I'm 90% sure we can do what you're talking about, but my brain's kind of falling apart. So I'll leave it at that for now.
Okay, we have two final questions. Hopefully your brain hasn't fully fallen apart. How do you handle something which is created on one device but destroyed on another? For instance, if I need to pass a linear lock guard or a ghost cell like proof token to a GPU. And also, since ARM has brought it back to life, how do we deal with hardware transactional memory and linear types?
Oh man. Okay, I'm gonna answer that second one first because that's I had no idea that hardware transactional memory is even a thing. Like I think I saw some papers on that, but I didn't know that was a thing yet. Um, so in Vale, I did explore kind of a software transactional memory kind of thing, because Vale used regions under the hood, and so there's this really cool thing where you could say um, that within this scope, this block. Uh, there's kind of an inside world, right, which is the code inside the block and the data created inside the block. And there's kind of all the data created outside the block that is reachable from the block, but it existed before the block. And one of the things that was cool about Vale, which I don't know if Mojo can do, and that'd be really cool if it could, is that the type system would track which data came before and which data was created within this block. And by the way, I didn't implement this in Vale. This is just like theory crafting. Like this could fall apart for a bunch of different reasons. But since the type system knows the difference between data created inside the block and data created before the block, then it could track any modifications that happen to data outside the block. And then it could, in theory, record those changes in a what I call a mutation list. And this mutation list would just be an ever-growing thing, right? Ever-growing, not a linked list, but some sort of like deck or a vector or something that would record all the changes to all the data that happened in this outside data. And then if a panic happens inside that scope, inside the block, it would just destroy all the data created inside the block, and it would go through this list in reverse order and undo every single thing that this one scope did to the outside world's data. Um, and how this interacts with linear types, this is another one of those things that I was like bashing my head against the wall for a week on. I'm like, oh wait, but what about linear types? If a linear type enters this block, and then like a panic happens and we destroy all the data created in the block, what happens? Turns out it's actually not a problem. It's not a problem because as we go through all of these mutations that happened and do the kind of undos, um, it'll naturally just happen that the linear type that was brought into this this scope would naturally be just ejected back out of the scope, just as a natural course of doing all these undo operations. So linear types actually isn't incompatible with transactional memory at all, I think. But of course, I'm assuming that hardware transactional memory works like Vale's region-based software transactional memory design worked. And like I don't even know if that's an apt metaphor. I don't even know. Okay, so you asked, yeah, your first question though was, how do you handle something which is created on one device but destroyed on another? So this one, yeah, a similar question to this one is how we handle linear types that start on one thread and end on another thread. And I love talking about that, but I only have 5 minutes, I think. So I'll keep this one as a TLDR before I answer your actual question. If we make a linear type on one thread and we want to send it to another thread, we need to make sure that it actually gets to the other thread, right? And it's not just dropped as, in an orphaned channel, which often happens in Golang. So what we do in that case is we make it so instead of having a single channel class, we have one channel is represented by two objects, a sender half and a receiver half. And the sender half, when we destroy it, it will send a linear, doesn't have to be linear, it will send a close message, right? The receiving half is the interesting one. The receiving half is a linear type that can only be destroyed if someone hands it the closing message that was sent by the sending half. And that, in a way, forces it to wait and read all the messages out of the channel until it gets to the final closing message. Okay, but it just read all of those, messages that were in the channel. And so one of those will be the linear message that we originally wanted to send from the source thread. So yeah, that's how we can kind of enforce that something happens over the thread boundaries. And I think something could kind of be done in that way over two machines. In other words, one machine would have a linear type that can only be destroyed once the sending half has correctly closed down their connection. And that's kind of the rough idea of how it would work. The big flaw in this is that this is the internet, and we're talking about TCP, and TCP is unreliable as heck, right? And it's like there's no way to guarantee that we're going to get any sort of close message, right? So we're going to have, oh, here it is, an escape hatch for when the connection is just lost. And designing that would be actually really interesting because how do you design the escape hatch, but also try and uphold a lot of the guarantees that we get from linear types? I think it's possible. I don't know. Every time I think something's impossible with linear types, I end up smashing my head against the wall for a week and finding out that it is actually possible. So I think there's hope for that one. Hopefully I answered that well. Okay, it looks like there's one last question.
I think that was all of them.
Oh yeah, just a last comment.
Yeah. Thank you so much, Evan, for the presentation and for answering so many questions. Let's all give Evan a big virtual round of applause. If you want to come up mute, won't force you. All right. So, do you mind stopping your screen share for a second, Evan?
Yeah.
Thank you. So real quick, we also have a little bit of Q&A today. We already answered the first question. Or we already answered this one for Evan. But the first question is, I believe Chris has mentioned the team was working on a roadmap. I was wondering if there was a roadmap for the roadmap, which is a very fair question. The short answer is that we are aiming to share something in December. The longer answer is that we're hoping to have more specifics in terms of the timeline for you soon. And we want to do this as soon as possible and really make sure everyone is on the same page regarding the roadmap within our community. So the other questions, Chris had a last minute conflict for today. So I want to give him the chance to answer the other questions. There were really great questions submitted. Those questions will be added to the agenda doc. I'll drop the link to the agenda doc in the chat as well, but I think most of you have seen it. And Chris will answer those async in the doc. But thank you everyone for coming and for the awesome questions and comments. Our next meeting will be in 3 weeks. So if you have any interest in presenting or sharing something in that meeting, please reach out on Discord. And thanks so much for joining. Bye for now.